Good day, sir. My name is Jaslyn, and today I'm going to present to you the introduction. The title of our process is called Production of 1,000 tons of ammonia per day. The first objective is to achieve an end product of ammonia that's 1,000 tons per day, and the second is to obtain a purity of 99.9%. The purity we intend to obtain is for the quality that we need in order to sell our product. Next, in order to make ammonia, the process is known as the Haber process. It's where 3 molecules of nitrogen reacts with 1 molecule of hydrogen to produce ammonia. This reaction is exothermic and it's irreversible. In this process, we use 5,000 kilogram moles per hour as a flow rate, total of both nitrogen and hydrogen. Next, our final product was kept in liquid phase in a cooler at negative 50 degrees Celsius. Now, there are many uses for ammonia. Most of the ammonia manufactured goes into fertilization. Lastly, there's an article by Model Intelligence, and it predicts that in the next 5 years, the compound annual growth rate of the global ammonia market will be 5%. And this is all based on the increasing demands of agriculture and production of explosives. So that's all for my part. Thank you.
Okay, hi, I'm Manji.
I'm Jun,
So today I'll be talking about the design methods for this case.
and I will talk about the function of unit operator involved in this process. So in this process, we will involve 5 unit operator, which is separator, reactor, heat exchanger, storage tank, and also the mixer. So the third is mixer. So mixer is a unit operator which mixing 2 or more components into homogeneous. So in our process, we are mixing the inlet feed gas and also the unreacted gases, and the product will fit into the converter reactor. So the second is a separator. So a separator is a unit operation in which it separates a mixture in different phase. So in this process, the separator is used for separate the liquefied NH3 and also the unreacted gas to achieve higher conversion.
Okay, so for the separator, in our case we use the general separator which separate 2 phases, because in our case we only separate 2 phases, which is the liquefied ammonia and also the unreacted gas. There's actually other separator, but we didn't use because, for example, 3-phase separators actually used for 3 phases, but in our case there's only 2.
So the third is a heat exchanger. So heat exchanger is a vessel which transfer the heat energy from one fluid to another. So it can be a cooling process and also the heating process. So in this process, we want to cooling down our product to 50 degrees C.
Okay, so for our case, right, we use the shell and tube heat exchanger and not other heat exchanger. For example, in UNISIM, there's actually a tube bundle heat exchanger and also LNG heat exchanger. For LNG heat exchanger, right, it's normally much more pricier and it's normally for a larger batch of scale process. But then for our case, it's not that big. Then for tube bundle heat exchanger, we didn't use because it's normally for higher pressure application. But for our case, we just use like pressure of 100 kV, therefore we didn't use, but we proceed with shell and tube heat exchanger.
So the next is reactor. So reactor is an enclosed volume which the chemical reaction will take place. So in this process, the reaction between the N2 and H2, we assume it is a conversion reaction.
So in our case, right, we are using the conversion reactor and not other reactors. It's because the conversion reaction type matches with the equation that we have, which we have the stoichiometry, and also we can assume the conversion is 90%, then we will be able to run it. Why we didn't use like different reactors is because, or reaction type is because like equilibrium or other reaction type, right, cannot fit into the conversion reactor and it will not run. So why we didn't use equilibrium reactor is because for equilibrium reactor we actually need those variables such as the equilibrium constant, which we do not have, and we cannot simply assume, as this will affect the final outcome.
So the last is the storage tank. So a storage tank is a container which hold the liquid or compressed gas for the short or long-term storage. So in this process, the storage tank is store the liquid ammonia and at a temperature of negative 50 degrees Celsius.
Hi sir, I would like to explain the results that we obtained for the production of ammonia 1,000 tons per day. So first had temperature, pressure and molar flow rate at 50, 100 and 5,000 respectively, and the composition of feed is 0.25, 0.75 for nitrogen and hydrogen, and ammonia was 0. And the next unit operation was CRB 100, vessel temperature, vessel pressure, vapor molar flow and liquid molar flow that is, and which is 535 degrees Celsius, 100 kPa, 3346 kilogram mole per hour and 0 kilogram mole per hour respectively. And next is E100 unit operation, which is they contain of tube side feed mass flow and shell side, tube inlet, tube outlet temperature, shell inlet temperature, shell outlet temperature, which is 6.738 times 10 above 7 kilojoule per hour and 1.01 times 10 above 4 kilogram per hour, 535 degrees Celsius, 50 degrees Celsius, negative 50 degrees Celsius, 1780 degrees Celsius. And the next is CRB 101 unit operation. They also got mainly talk about the conversion graph. The result of actual conversion was 90% under the base component of nitrogen injection 1, and the graph shows as like the sketch of this, like this. As this increase, this is also increase.
Hi, I'm Kitana. Today I'm going to talk about analysis of our ammonia production. Many modifications can be made aiming for increased energy efficiency, higher production and lower operating costs. These can be achieved through several implementation of better process conditions and equipment design. The energy efficiency can be increased through tight control of H2 to N2 ratio and optimizing the purge gas to optimum conditions. The production rate can be increased through minimizing plant downtimes. During this process, several emissions need to be monitored, such as the emission of syngas, flue gas and also purge gas. Okay, let's say when our production of ammonia is initiated, there are chances that ammonia gas can be released to the environment when there's a leakage in this equipment. This can greatly affect the health of many, so these gases needs to be treated and they are routed back to the primary reactor as fuel gas. So that is all for my part. Thank you.
So as mentioned previously, our target is to produce 1,000 tons of ammonia per day with a purity of 99.99%. So next, I will show you the PSD of our process. Let's go!
So basically, this is the PSD for our process. As you can see from here, the feed, we have composition nitrogen 0.25, hydrogen 0.75, with the assumption of 5,000 kg mole per hour to produce 1,000 tons of ammonia per day. So the mixer is actually mixed with the feed inlet and also the recycle stream. The product is then enter the first conversion reactor. As you can see, the inlet temperature is 108.7 degrees C, while the outlet temperature is 535 degrees C, which means this process is happen at exothermic, where it releases energy. So in order to separate products and reactant, heat exchanger is needed. And the product is then enter heat exchanger where it produces two streams, cold stream and hot stream. Hot stream is enter the second conversion reactor where products is entering the mixer for recycle. Then the cold stream is then enter the liquid vapor separator, and the product is then enter the final letdown separator. Both of the top stream of separator are combined and go back into the heat exchanger. So the final product will then store in the storage tank. As you can see from here, the mass flow rate is 1,000 tons per day, where with the composition ammonia 0.999993. So it's eventually met with our target.
So as a conclusion, we finally met with our target! Yay! So the process actually produced 1,000 tons of ammonia per day with a purity of 99.99%. So this is actually the most economic way where it conserves energy and it also reduces the cost at the lowest. So yeah, thank you for watching and bye bye!